Welcome, everybody, welcome to the ICT Research Day webinar series. I'm so glad that you could join us. I'm Dr. Judy Farvolden, and on behalf of the ICT team, I welcome you to our ICT Research Day, and thank you for joining us. I'll be hosting the webinar series. This session will be recorded and shared, and chat has been disabled, so please use Q&A for questions at the end of the presentations. I certainly hope we have time for your questions, and I certainly hope that you find our presentations interesting, so please find Q&A on your screen and enter your questions there. iCity Urban Informatics for Sustainable Metropolitan Growth is a project led by Principal Investigator Professor Eric Miller at the University of Toronto, and I'm the project manager. iCity is a highly interdisciplinary and collaborative program among researchers at 3 universities, the University of Toronto, OCAD University, and the University of Waterloo. We are grateful for the support of our public sector partners, Waterfront Toronto, Transportation Services at the City of Toronto, and the region of Waterloo, and by private sector companies Esri Canada, IBM Canada, and Celent. We could not have done it without their support, both financial and in many forms of co-creating and collaborating. iCity is funded by the Ontario Research Fund, Research Excellence Round 7, and we are also grateful for ORF's support of our unique project. iCity research is organized around 3 themes. Theme 1 provides a foundation of ontologies and platforms, the subjects of today's talks. Theme 2 comprises a set of urban transportation applications in street design, parking, transit, transit-oriented design, and integrated transportation and land use. And Theme 3 activates our applications with visualization and decision support tools created by partners at OCAD University. This is the first of a series of presentations, and I hope you will join us for the others. You can register for the other presentations, any and all of them, at utree.utoronto.ca, the Utree website. As I said, Theme 1 provides a foundation of ontologies and platforms, and that is the subject of today's talks. I'll briefly introduce the speakers, and you can find out more about them on the Utree website. We begin with a talk by Dr. Megan Katsumi. Megan, please join us. Megan joined the iCity team after completing her PhD with the Semantic Technologies Group at the University of Toronto. Megan's research is concerned with the development of a set of ontologies and reasoning services to support city services. Megan has been with the iCity project since its inception, creating a foundation that unified our projects across data. And over to you, Megan. I will stop sharing and let you take over.
Okay, thanks, Judy. Continue. Okay, thanks, Judy. Thanks for the introduction, and thanks to you and Pat and everyone else for organizing this. I'm really happy that we're still able to share the results of this, several years of work with everybody today. So without further ado, I'll just kind of go back to this really nice overview that Judy gave earlier. And this serves as a little bit of an advertisement for some of the other sessions in the series of talks, but just by kind of re-emphasizing that this was really a broad project that covered lots of different areas, some of the research going on looking at things that like complete streets design, parking management, transit management, land use, and so on. And in our part of the project, we were tasked with the ontology design, really looking at how we can support the data layer of urban informatics. And doing that, we were looking at the data that was generated and used by all of these other projects, things like the simulation projects and parking studies and so on, and asking ourselves the questions, how is all this data related? Can it be combined? How can it be shared? And so on. Before going any further, there's a really important question to address. What's an ontology? So those of you who are not strangers to Research Day may be somewhat familiar with this already. which is great. If not, we'll spend a little bit of time on this now before talking more about the project. So informally, an ontology is a kind of specialized model. It's something that looks at the core concepts and properties in a domain's data and asks to what extent can we generalize them in a useful way. It also looks at the key distinctions between these concepts and can we formally define these concepts and these distinctions. Ontologies do this in a precise formal representation that's machine interpretable. So they can be used as reference models for the domain, but they can also be applied for much more than that. They can be used to support the reuse of data, data validation, semantic integration, as well as inference. As a short example of this, we'll consider the concept of a root. So here we have two different definitions of a root in two different contexts. So in the context of a simulation, we might define a route as representing a possible path of travel that begins and ends at some nodes, connecting the network by accessing some set of arcs of interest. In a wayfinding service application, we might consider the definition of a route as something that also represents a possible path of travel with a start and end, but maybe in this case, we're more concerned with its associated geometry. Now, in an ontology, these concepts can be defined in a formal logic, as we've shown here in the slides in description logic. And that formal logic really clearly identifies the properties of interest as well as the classes of interest. And it does it in a way that has a well-defined semantics as well as well-defined set of inference procedures that goes along with it and supporting tools. With this kind of representation, we're able to encode the data of interest with a semantics by mapping it into the language of the ontology. So for example, if we have two different data sets, one talking about a travel simulation set, routes, and another talking about routes in a wayfinding application, we're able to map both of those into the language of the ontology using something called a semantic mapping. So for example, we could say that this first column here, ID, represents an instances of a simulation route. We can define attributes of the simulation route. And using these sorts of mappings, we're basically describing how the data should be interpreted in the language of the ontology. And we can apply tools to generate something called a knowledge graph from these mappings. And essentially that's an encoding of the data in the language of the ontology, which allows us not only to formalize the data in a way that we can access it, but to do it in a way that actually integrates, in this case, the concepts of a simulation route and a wayfinding service route. So here you see we have the same data that we had in the tables, but it's now encoded using this shared vocabulary, has a route 1, 2, 3, 4 is a type of simulation route and has an end node and has a start node and so on. Encoding the data in this way, we're able to capture different kinds of definitions of a route in this example, and we're also able to explicitly identify how different kinds of these concepts are related, what's common between them, what's different between them. And this also means that data sources using either definition can be understood and captured in this sort of integrated knowledge base, which can then be queried in a federated way. Beyond this, we can also use this approach for data validation because the ontology is capturing constraints on each type of route. So data that's encoded in with the ontology can now also be assessed automatically. We can verify or validate whether a particular data point conforms with the definition of a route, and we can also apply automated reasoning tools to infer new facts about routes. Beyond this, the ontology also improves our opportunities for data reuse because you can see that any data that's been encoded or mapped into the ontology representation also now has its meaning embedded. So now there's no longer a question about whether or what that particular column means. It's explicitly described in the knowledge graph. For the iCity project, we developed something called the iCity Transportation Planning Suite of Ontologies, which is essentially a set of different ontologies that has been developed and implemented for various transportation planning activities throughout the course of the iCity-ORF project. So here we've grouped them according to their domain. So at the bottom, you can see the set of foundational ontologies where we're defining concepts like activity, time, and location. Then there's a set of ontologies that focuses more on the characteristics of the urban system, things like the buildings and land use and so on. And then a set of ontologies that focuses more on the behavior within the urban systems, things like transit, trips, and travel, and so on. And so now one observation that we made, and I should mention, if I don't mention later, that all of these ontologies are available online. We've also published a detailed report of their application, and then more information can be found on the iCity website, and as well as our own project GitHub. So one observation that we made during the course of this project is that data integration wasn't a challenge that's specific to the iCity project. It was something that was really faced by the transportation planning community in general. And this observation led us to the creation of a multi-part ISO standards projects focused on the creation of a city data model. In the general context of transportation planning, the data problem really amounts to data silos. So we have data that's collected from silos and then oftentimes ends up being processed into more silos. We found that data, although it can be very expensive to maintain data and expensive to actually generate and through these analyses, more data, unfortunately, oftentimes this data is not reused between projects. What complicates things further is that we have a multitude of different transportation planning tools that are in use by different researchers and in different cities. And because we have no easy way to compare the results because each of these tools has their own unique data models. So our takeaway from this was really that a standard for all this data is needed. And although there are a lot of existing standards out there, most of these standards overlap with the domain but don't cover the domain of transportation entirely. And in addition, many of these standards are subject to some kind of ambiguity despite their detailed definitions. And I'd like to spend a little bit of time talking about that ambiguity now. So as an example here, we have an excerpt from the GTFS. The GTFS is something that many of you may be familiar with. It's the General Transit Feed Specification. So this is a common format that's used to capture and share public transit data, so things like bus schedules and locations and so on. It's highly successful. It's been widely adopted all over the world. It's really great. And here we have just an excerpt of that that's looking at the stop times file. So essentially what this is when you have different transit routes, within each route you might have a series of trips, and the stop times file allows you to specify for each trip, so for each trip ID, what time is that trip expected to arrive at and depart at a particular stop. Essentially, there's some other attributes there as well. But it's pretty straightforward, and you can see here there's detailed descriptions of each of the fields. There's also examples available online and lots of resources. But so my question to you is, okay, so what about loop routes? How would you encode the stop times for a route like this using the GTFS? And it won't make you sit and think about that, but it turns out, jumping to the answer, there's actually two different ways of representing the stop times file for a route like this, and both of these ways are consistent with the GTFS. So you have option A, where you specify the times for A, B, C, D, and in option B, you're specifying the times for stop A twice. And this is something that's not explicitly been addressed in the reference, but it has been identified as a special case in a subsequent best practices document. In the best practices document, they indicate that the recommendation is for you to go with option B, which is to specify the stop, the information for stop A in this case, for example, twice. But really, the issue is that, or the potential issue is that both of these options is potentially consistent, is consistent with the GTFS specification. So this is, I want to make clear, this is not a criticism by any means of the GTFS. It's a really great reference that has been shown to be very useful. the point of this is really to illustrate this inherent ambiguity that we have in approaches, in traditional approaches to standards and similar specifications. And with this traditional approach, we have usually really detailed documentation, modeling languages to make things more precise, but these tend to focus on data structure as opposed to its semantics, which means that the meaning of a lot of these terms ends up being grounded in natural language. And this ends up leading to challenges because natural language is inherently ambiguous, can't get around that. And what this means is that we have then later a need for supplementary material to resolve these individual issues as they arise. Things like examples and best practices. The issue with that being that we can't predict or detect all possible ambiguities. So eventually what we have is differences in interpretation leading to differences in adoption, which will eventually impact the standard's effectiveness. So given all this, we propose that ontologies, and in particular the iCity ontology, provide a way to address both this data challenge for transportation planning, as well as this limitation of traditional approaches to standard specification. In particular, because the iCity ontology has a unique interpretation, which means that it has an explicit and unambiguous encoding, so it's not going to be subject to these issues of ambiguity. And also because of the added benefits that ontologies work with different tools, different data formats, support dynamic domains, and can be implemented for other applications. So beyond just specifying the standard, we can do reasoning and data validation and things like that. As an initial effort towards this, we have been working on the development of a series of standards projects as part of ISO-IEC Joint Technical Committee on Smart Cities. So these are city data model standards, and it's a multi-part standards. The first part looking at foundations, foundational concepts. So it will be comprised of a set of foundational ontologies defining concepts like time and space and so on. And following that, there's the city level part of the standard that looks at city level ontologies. So these are ontologies that cover concepts specific to the city domain, but generic in the sense that the data that they represent could be used or consumed by multiple different areas and services within the city. Then beyond that, we have the additional parts of the standard that look at specific city services, the first of which will be a standard for transportation planning. So the first draft of this standard, as you can imagine, draws heavily from our work with iCity, and it's built on the foundational level as well as the city level of the standard, and then extends that with the concepts or ontologies to describe the transportation network, transit, travel cost, and so on. And so just to finish up, I want to address the topic of standards collaboration. So as we're working on development, kind of continued development of our work in iCity as it translates into this standard specification, a really big consideration is this idea of collaboration between standards. So what I mean by this is we're creating a standard to address the challenges that we're facing with that data silos, but how can we avoid creating yet another silo that restricts data within the realm of transportation planning? So there's really, I think, a big need to collaborate with other standards groups in order to understand how the definitions that we're creating relate to definitions of overlapping concepts in other domains. And we created a global collaboratory to help us do that, which is what I want to just focus my remaining time on. So the iCity, or the City Data Model Collaboratory, is a website that's online right now, and we've created it to help us to develop a global consensus on this city data model. The purpose of the website is to enable us to identify concepts and definitions to be included in the data model, but especially importantly, to align related concepts across different standards, different related standards. So the website supports all registered users to, well, anyone can access the website, I'll start by saying that, and browse and review content. Registered users are able to comment on existing content and suggest changes and revisions. They're also able to propose their own terms and definitions, as well as submit use cases to help explain or justify terms and definitions. How the proposal process works is basically that anybody can propose a new term, and once that term has been proposed, it becomes open for the specification of definitions from the community. So for example, root here, once root has been proposed, then all users can kind of log in and propose their own version or their own definition for the term root. And these terms could be independent of one another, and they can also be proposed as specializations of existing terms. These proposed definitions must be specified in a formal logic to avoid the issues of ambiguity, and they must be accompanied by a use case. This requirement is to ensure that the rationale or the need for a particular definition or term is clear, and they're then subject to community review. The last really important thing I want to emphasize is that multiple definitions are allowed and expected in the collaboratory, and the point here is that the point of this website is not to kind of force people to agree on a single definition of each term. The point is to collect all of the different definitions that are out there and try to understand how they're related to one another. So once the discussion of these definitions has settled and we've agreed on that these definitions are in fact correct and represent what we mean, then we'll go through them and identify what we call the minimum viable definition for each term. So minimum viable definitions are something that's identified relative to a set of definitions for the same term. And essentially they tell us what the minimum semantics required for a term are. So what's the semantics that's been shown to be shared between each definition in the set of definitions for a term. And these are really valuable, or will be really valuable resources, because they tell us they clearly identify what the shared meaning is that all stakeholders have in common regarding a particular term, and as well as identifying what the set of properties is that's shared amongst the different definitions, and identifying the distinct definitions as subclasses of this minimum viable definition. So in the example that we saw earlier, the root class shown in blue is playing the role of the minimum viable definition. So you can see it clearly identifies that between the different definitions of root, simulation root, as well as wayfinding service root, we have both, they share this semantics that a root must have a start and an end node. And that's the property that's shared between them. And we can also clearly see what the difference between these classes are, that the simulation root acts as an arc, whereas the wayfinding service root has some shape associated with them. So this is something that we really think is going to be valuable in identifying the relationships between each of the standards. And I just kind of want to wrap up here by saying, again, encouraging everybody to please check out the website, check out our project on the iCity website. And we would welcome any feedback, and as well as your participation. And of course, any questions that you may have now or offline. So thanks very much. And I'll give this back to Judy for questions.
Great. All right. Thank you, Megan. Thank you very much. I think we all better hope that when data is being exchanged between apps in the Internet of Things, that it'll all be consistent, and that Megan's work under the supervision of her Mark Fox in the Department of Mechanical and Industrial Engineering is going to be a really long-lasting legacy of the iCity project and the work that they've done with standards and their global collaboratory. So thank you, Megan. We have time for a couple of questions. So I'm going to ask you, who's been involved with the standards collaboration efforts to date?
Yeah, so right now, as of right now, we've been involved in a couple workshops with the W3C, which is the World Wide Web Consortium, and they're sort of the governing body for a lot of the standards that you see on the web right now. And through that work, we've also been working with groups, other groups within ISO, so involved in TC204, like the ITS standards groups, as well as some groups from OGC, which is the Open Geospatial Consortium. So basically right now we're really just trying to reach out to different standards groups in areas that will be overlapping in some way with city data and transportation data, to get their involvement with the collaboratory, their feedback on the approach, and really try to make sure that we're not repeating other work and creating more silos as we're going forward with this effort.
Yeah, like another standard, and already has one. Can you mention how the ontology has been applied so far?
Yeah, so I think I only had really one slide on this in the presentation, so I'm hoping that people will go look at the iCity website later, but also, so there's a pointer from there, as well as a brief description of the project there. There's a pointer to our GitHub, which has all of the ontology files, detailed report kind of going through each of the modules, as well as describing throughout the iCity project how the ontology was applied. So we've kind of worked with different research groups on different case studies, and also an advertisement for myself. We'll be talking more about one of those applications later this week, I believe, with some of the work that we did with Esri Canada. So lots of different projects that kind of informed the design of iCity along the way, really.
Exactly right. Later on the same week, and we'll talk about that a bit later. And as I introduced you, we mentioned that you're interested in applying the ontologies to city services. Are you done with transportation, or what's next?
Well, I wouldn't say we're done. We have a good start. So the standards that are referenced here, I believe, and I don't know if Mark's on the call, but I'm sure he would be able to verify, but the standards have all been approved. They're no longer proposals. They're now new standards projects. So it's, you know, I'm sure we still have work to do within the transportation domain for city services, but we'll also be looking at extending this city data model standards to include other areas. We have maybe some upcoming work in the water services area side of things as well.
Yeah, so it's been, well, Megan has been with us since the beginning of the iCity project when we kicked off in 2015. We've been going on it for 5 years, winding up June 30th. And Megan has tirelessly cycled around working together with the other postdoctoral fellows on this project to be learning what it is about their specialty and what it is about their data, and enfolding that into the ontology work that she's done. And it's a process, I would say, a big process. But after 5 years of work, we see, you know, amazing fruits come out of this. And as I said, I really am excited about the standard. So there was a lot of work done on this project. And if you will take a look at our brand new iCity website, and you can find that at icity.utoronto.ca, you can find out more about this project. It's an archive of all the work done in this project, the people, publications, and presentations that were undertaken here. And I encourage you to check out the iCity website for more information about iCity projects, including the ontology. Megan, thanks very much.
Thanks, Judy. Thanks, everyone.
Great. Okay, next up in our presentations on ontologies and platforms is the platforms. We have 3 speakers here to speak with us about the iCity ITSoS platform and ATIS applications. First, I'll introduce Dr. Hasan Bayanouni. Hasan joined the iCity team as a postdoctoral fellow of iCity ITSoS. He has 13 years of experience in the ICT industry, where he led mega projects in ICT infrastructure and smart cities. As iCity has been winding down, Hasan has been engaging with new initiatives at the Smart Freight Center, namely taking a leadership role in the freight data warehouse and data analytics solutions. Hasan, please join us. Ahmed Aqra joined the iCity team after completing a Master of Applied Science and Software Systems Engineering at the University of Regina. He is now working towards his PhD in Intelligent Transportation Systems at the University of Toronto. His research focuses on developing trip-level and link-level traffic assignment that will pave the road for a network-wide trip-level in advance reservations platform in our transportation system. The Regina connection continues. Mohammed El-Darieby is a professor of software engineering at the University of Regina. He has more than 25 years of experience in software development. He is widely published in the areas of software and networking systems with applications to smart infrastructure and city dynamics. Over to you, Mohammed. I'll stop sharing and let you take it from here.
Okay, hello everyone. The three of us, Ahmed, Hasan, and myself, will be presenting a summary of our efforts within the ICT project. And all of this has been done with collaboration from the Professor Bayanouni Abdelhai, who's in, at the Artery Transportation Center at the U of T. I'll focus my talk on a smart city platform and a set of city services that we've developed within this project. If you can go to the next slide, please. Yeah, so the main challenge for this project was trying to develop a set of management services for the next generation city applications. We do see the future of such applications to involve many functional services and to be processing tons and tons of data that are generated from all the sensors out of the Internet of Things. This is in contrast to the what we see in the contemporary city apps. Basically, they are composed of one or two services and processing one or two data sets, and mostly developed by siloed business entities. The future is going to be different in our opinion. Those services developed by those different business services can be integrated into way more sophisticated applications, and those sophisticated applications will be processing way more data than what we're currently used to. And these applications have to really be applied to a scale of a mega city such as Toronto. Go to the next slide, please. Here is an example of those next generation apps, and this is based on the ITS architecture, and this is just a snapshot of how the ITS architecture has seen the advanced traveler information systems. As you can see, the one app is decomposed into many services, and we've just listed 5 here for your reference, but there can be way more than this, and each of those services processes a set of data, and we've listed here a few. In my opinion, very limited functionality of this vision is currently implemented in the ATIS applications. And our task in this project was to try to think of the future with so many more providers of services and data sets, and how can we work with those to integrate those data sets and process these services and process the data sets and link them, and also integrate the services into larger workflows that achieve such a vision for the ITS architecture. You can go to the next slide, please. So the idea that we have for the platform is to the right. This is basically what we worked on. To the left is the general architecture of a smart city application. For us to envision this, we were thinking of developing in this project a set of platform capabilities to manage the services, the multitude of services that we envision to be provided in the future, as well as to manage the humongous data sets and the various and heterogeneous data sets of the future. And a main component of doing these management at the service level and at the data level was to develop ontologies, which we define as a knowledge representation. So basically we capture the knowledge of humans into ontologies, and this would help automate the management of the different services and the different data sets. You can go to the next slide, please. So in this platform, we've developed 2 things basically on those two dimensions that you see at the bottom. We've developed those capabilities for the service management and for the data management, and those you can find them on the right. And we handled smart planning of services and smart composition and selection of services. And we also worked with volumes of data, large volumes of data, and different variety of data and different formats, different access methods, and so on and so forth. And to the left, we've also developed many of the services that we described, and those services process those data. And we're going to be starting this, or we're going to first, for the rest of this presentation, we're going to show you some of the demos of these services. And then Ahmed and Hasan will be doing that. And then I will talk to you again after they're done to quickly describe a little bit of the platform capabilities that we have developed. On to you guys to demo the services.
Right. Thanks, Prof. Mohammed. Now, to what we did actually, we built the ICT Integrative Platform, or ITSoS ICT Integrative Platform. And to start with that, we built the foundation services. Actually, the foundation services that we start with, actually, we start collecting the data. But that's why we start with 3 different sets of services, or we can call it the first one. It is the traffic data as a service. We build the data lake actually for all traffic data that has been collected during this project. Then we moved, after that, we built another abstraction service, mainly called for trip network abstraction service. And thirdly, actually, we collected the GTFS data, and we able to provide it through the ITSoS platform as a service for different services that we will discuss it during our presentation. Then we built the 3 different pillars, or 3 different services pillars. Actually, we will discuss it in details during our presentation. The first one, it is GIS visualization service, has been built with Esri. Mainly, we'll discuss 3 different services. The first one is pedestrian safety index. The second one, the origin and destination travel time. The third service, actually, which is the travel bottleneck visualization service. Then the second pillar, actually, it is the trip services, where multiple services have been introduced. Trip routing, trip link and level state tracking, then a trip level reservation, actually. And the third pillar, actually, there is performance management as well, has been built as a service within the trip services. And the third pillar, actually, there is different services related to the ATIS. Mainly, we have an open trip planner transit services. And then we built something with collaboration with Theme 1.1, with the Ontology team, with Megan, where we built the OTP based on the ICT Ontology engine. The last one, we have the high traffic microscopic characteristic estimation using CNN. This is one of the services that has been built. I will give you like a quick overview about those services. We already did a recording for a short video just to talk, to take you with a quick, to give you an overview about those services that has been built. And you can find all those services that under ITSoS website, which is itsos.ca. We do have multiple visualization services has been built. The first service, actually, the origin and destination, the data that has been collected from TTS data, actually, Toronto Tomorrow Survey, where we collect all different origin and destination, and we're able to understand and calculate the travel time index for between any origin and any destination, where any user, he can log in there and he can select the city that he would like to choose. He then select the origin and he select the destination, and he can decide what type of data, or if it's installed without toll. The second service, actually, it is the bottleneck services. Mainly, we build it for the 400 series highway within GTA. We are able to calculate the travel time index across the whole 400 series highway, and where we are able to calculate it in 2 minutes and in hourly basis, which will give an indicator for the historical data has been collected from MTO data, actually, using from the roof detector data. The last service has been built, actually, which is, we call it the pedestrian safety index, where we are able to understand and do correlation between the number of accidents that we do have across different intersections, and we are able to represent it on the map, actually. Sorry, it went very fast. And those services, just I need to go a little bit back, a little bit here. we built something called data module or the data lake, where the users of the solution of the ITSoS website, they can log into the data module, they can extract the data after signing the NDA. And those services has been published with collaboration with our partner, Esri partner. We are using the WFS publishing services, where all those services has been published online, actually. I would like to hand it over to my colleague, Ahmed. Sorry.
So thank you, Hasan, for the introduction. In this part, I will take part of these services, which is related to TRIB. TRIB is a reservation platform, ongoing research that I am currently doing in my PhD research. In this specifically, these foundation services, I will concentrate only on network abstraction services. These services will enable TRIB, which is the reservation platform that we are now building a proof of concept for, include TRIB routing, TRIB link level state tracking, and reservation and performance management. So I want to concentrate in my presentation on link level and TRIB level. So I will be using these terminologies many times, and this will justify why we need network abstraction services. So in the next slide, I will present a comprehensive framework for TRIB level and link level network abstraction. This is only related to supply and model in supply and demand modeling for this section of the presentation. We have many for routing, reservation, performance management, network state tracking, but in this presentation, I will only go over the supply and demand modeling. The objective of this exercise is to build ready to integrate tools that will be used in future when we have pervasive connectivity, mobility as a service, and more automation to control our traffic on a TRIB level and link level way. These tools will be integrated with those traffic management solutions, and also with transportation simulation platforms like, for example, AIMSON or any other transportation simulation platforms. In the next slide, this is a snapshot of these tools. We have it for supply modeling and demand modeling. In supply modeling, we have many tools. I will just concentrate now in topology building tool. The idea is the need to have, we need to abstract the network. So the abstracting the network is how we will see every link as an entity, every node as an entity, every traffic item like a traffic signal sign also as an entity to maintain all attributes of from different data source or map sources. So in the next slide, I will have this example for topology building. So if we just think about OpenStreetMap, so we already have the OSM data for GTA. Then we combine these data with Ontario Road Network. This is a map network that provided by the province. It's called LOI. And also we have centerline data, which is street information, geometry information, which are taken from city level. So we used the data from Beale region and from City of Toronto. And also we have our model for the GTHA, the AIMSON model. So the map abstraction tools take all these data sources together and abstract them in one database that include data for road and data for road link and data for nodes. So for any road or for any GPS coordinate, we can see that this road if it's in the border, for example, between two cities, that this will be available in centerline data from Beale region and from City of Toronto. And those, this road link will have this ID. And the same road link will have another ID in OSM and have a third ID in Ontario Road Network. So the objective of this exercise is how to deal with these plenty of information that is available from open sources and how to aggregate them in a way that we will fix them and validate them to be used for future. And we apply this as for TRIB as a traffic reservation system. So in the next slide, I'm having this example for TRIB as Advanced Traveler Information System. So we use this network abstraction tool to, so on the right side, we have TRIB, and then the left side is live data from Google Maps. So we choose an origin and destination, and then we use Google Maps to generate a path, and then we use a TRIB as Advanced Traveler Information System using the network abstraction tools that we built. So now the question in the next slide, that why we need a network abstraction. So why we not just use a Google as Advanced Traveler Information System, and that's it. So the idea, and this is the screenshot will explain this in detail, that what if we need to prevent the traffic from a specific link? What if, for example, in this case, for those familiar with the GTA map, how if we just exclude a link in 427 because the link at that time exceeds its capacity. So how we will make this work? So this is the rationale behind the TRIB, is how we will have at link level and the TRIB level traffic control. This will be more applicable for in future when we have AVs on our street. But this is now what TRIB works. So in the coming video, in the next slide. So this is a screenshot of one screen of the TRIB, just to show the origin and destination. So we pick an address in Mississauga, and the destination is the UFT. So this is the TRIB, how it works. So think about the traffic control system that will pick a link in 427. So this is now in TRIB. So we are picking and selecting a link in 427. And we decided to prevent the traffic to go there. And this is now, we are doing this only for one link, so in 427. So the TRIB now will do rerouting and will avoid and prevent any traffic from going to 427. This will come with cost. So if you see the travel time will be, instead of having 40 minutes, we'll have like 43 minutes. But this will give the cities in future more control on our street. And this will be done dynamically for thousands of links at every time step. That's it for me. I will hand it over back to Hasan.
Thanks, Ahmed. Again, back to the ATIS, we would like to continue. And one of the services under ATIS, which is the transit service, which is the OTP, has been built on top of the OTP, the Open Trip Planner. Actually, we built also on top of the OTP that we build the transit services for across the whole GTA, but we took an extra mile actually with collaboration with the theme 1.1 with Megan, where we introduced the iCity Ontology as an engine to be a middle layer between the data that has been collected with the GTFS data and OTP as an application. This is one of the first applications that we use on theme 1.2 by using the iCity Ontology, where all data that has been represented and consumed by OTP using the iCity Ontology. We did the proper referencing for the data and representation, and we linked the whole data that we do have using the iCity Ontology. And the users, when he's using the OTP or the advanced traveler information, specifically the OTP part, which is the transit part, actually everything has been generated and the data has been generated and consumed using the iCity Ontology. Then we came out with the advanced traveler information, which contain built on top of two components. The first one, the semantic OTP instant and the trip instant. The first instant, which is the OTP instant, it is mainly for the transit, and the second one for traffic or the car way of travel. And where the end user, he can log in for the tool, he can use it, he can choose if he would like to use traffic or he would like to use a transit, and he can use one of both, or he can use both of them to make a decision how he would like to plan his trip actually. And this tool already has been published on the top of ITSoS platform, and users, they are most welcome to test it and to use it as well. Let me hand it over now to Prof. Mohammed. And now, before that, the ITSoS, it is an integrative platform. All users, all attendees, they are most welcome to have a look for the tool, to the platform, to visit it actually. It is itsos.ca, the website. They can contribute to the website, they can build their own services. Actually, we define a methodology how we would like to publish any services on top of ITSoS website or platform, where we need to define the problem at the first stage. Then we have a look, we need to look for if the data is available based on our stored in the data lake. If we can use it, we can consume it. If no, we need to think how we need to collect data, how we need to integrate it and ingest it inside the data lake that we do have. And then we need to look on details, how we'd like to analyze the data and visualize it. We have already, thanks for our partner, Esri Canada, there is part of the platform or the integrative platform, we have an Esri component as a main pillar for data analytics and data visualization. Then we can share the services online, and we can see how we can integrate this service to be part of bigger application, and how we can consume the data and represent it using different applications actually. Now, if you allow me, I will pass it to Prof. Mohammed El-Darieby for the next slides.
Ahmed and Hasan have presented a few of the services that we've developed here within the iCity project. And what we're anticipating in the future is that more and more and more of these services would be developed from different business entities and different providers. And what we've developed within this project is a service discovery and composition module, basically a software that looks around the network and looks for published services from different providers and uses ontologies to discover the capabilities of these services. And then the module would be able to pick and choose the services that meet specific goals of users and form an execution workflow that gets executed through discovering data sets and processing data sets from sensors and from other data sets that are available on the internet. And again, through processing ontologies, we would be able to process those data sets and produce results at the end of the execution of the workflow. And some of these capabilities were developed and published in journal papers out of this project that we're working on. If we can go to the next slide, please. One specific part of this was to work or to build ontologies in collaboration with the iCity project that was led by Dr. Fox and Megan. And Megan just gave a presentation on and build sophisticated ontologies from different data sets that are listed here. Ahmed also spoke about grouping together different data sets in his trip reservations. And we group these, although they come from different providers, and they have different heterogeneous aspects in terms of access, in terms of format, in terms of even naming of columns and naming of databases. We worked in this project on integrating and linking those data sets. Next slide, please. And the last thing we worked on was trying to build these capabilities of service and data integration and expand them to the level of a mega city where there is tons of information. And this video, I'm going to be showing you another origin destination calculation module that basically scales very much to the size of Toronto and can also consider historical data of Toronto. If you can play the video, please. For us to do this, we worked with the newer or the contemporary big data architectures
Welcome to
that takes.
Today I'm going to walk you through the basic features of our project.
We can go to second 35, please.
Express is able to display. Next, we look at Toronto.
This with the
Input a starting position and destination into the routing engine. The map will resize to display the optimal route based on the current traffic model. The trip time is calculated using real-time road speeds. The base maps for our project are provided by Mapbox and Esri, and the layer view can be changed using the interface. When the layers are changed, the map is redrawn from the tile server. Esri integration is a key feature for integration with our customers' other projects at the University of Toronto. Finally, we can demonstrate live routes being generated from the routing engine in real time. Our server has an approximate delay of 20 milliseconds per route calculation in the City of Toronto. When a route's generated, the server will often present two valid routes, allowing the user to switch between them if required. Once a route's selected, you're free to drive.
So again, next slide. Yes, we use this very scalable architecture. We used a lot of parallelization and in-memory processing as per the big data standards that are currently available. And this allowed us to calculate routes, and as you've seen in the video, real-time calculation of the routes within very fast time frames, considering larger amounts of data. If you can go to the next slide, please. This is a summary of our platform. We really see that we've done a lot of service development. We used a lot of intelligent and smart capabilities. We've also integrated a lot of data and services, and our platform is also performant because of the big data architecture. Sorry I took so much time. Judy, if we're more than welcome to answer any questions.
Thank you all very much for that presentation. I have just a couple of minutes here, so I'm going to reach. I have one question for Ahmed. And when you talked about the network abstraction tools and you were applying the developments you have on ITSoS to some novel applications, what about really novel applications like AVs and connected vehicles? Is it extendable, useful?
Yes, so the network abstraction is considered as a foundational type of services that will serve different applications. In my research, I'm using this for trip reservation and control. So this will be like a network-wide traffic control system that will use network abstraction as a tool to control a link level in a network. So this is, I think, will answer the same question that we are seeing in question and answer. What is the value proposition here compared to Google Map? And this is the main idea. So think about City of Toronto. If the city want to control a specific link in a specific ramp or specific link in a highway, so they cannot use Google Map because Google Map is like a black box, so you will not be able to use it to control the traffic at specific link. You can know the travel time using the Google Map API, but you will not be able to prevent a reservation to come through a specific link in a highway or on a ramp. So this will be considered a value proposition here for a trip, comparing with Google Map, giving the traffic control department and transportation management department cities a way to control the traffic on every link in our city.
And to manage this like a transportation system of some kind.
Yes, so this will be integrated at link level and trip level with different transportation system for traffic control, traffic monitoring, traffic management, and the same for transportation simulation system. So this is even for researcher where we need to predict or estimate or simulate, in this case, what will be going on if we implement scenario A, scenario B, so for any sensitivity analysis. So this can be done to give more control to practitioners in this field and even for the ITS engineer to control our network and transportation systems in future.
Well, and traffic is coming back. If you listen to the traffic reports in the morning, they do have something to say again. Right? So you will see what the future will be when we have trusted data with consistent meaning out of ontologies that can be used for novel transportation planning and control other applications. So thank you very much, guys. As before, the very short talk you saw today represents the culmination of the work that was undertaken over the course of 5 years in this area. So again, if you'd like to find out more, I turn you to the icity.toronto.ca website, our new website, and you can find out more about the people, publications, and presentations that underlay this work at that place and that time. Thank you very much. This has been the first of our seminars in a series of 5 that we're hosting over the course of iCity Research Days. We wish we could be hosting you in person, but we're delighted to be able to host you virtually, and I hope you'll be able to join us. On Wednesday, we'll have a session on the early work and visualization in iCity, followed by Friday and Monday, some of the urban transportation applications that I mentioned previously that we'll be working on. And finally, on the next Wednesday, we'll wind up with a talk on the value of infrastructure investments on land value, and next steps, which is a preview of our work, which we are calling iCity 2.0, Urban Data Science for Future Urban Mobility. Again, these talks were being recorded and they will be shared with you. I hope you will join us again. Thank you for joining us today. Be well, be safe, and I look forward to the day when we can see you again. But until then, I hope to see you back at our seminars. Thank you very much.